Hello, this presentation will talk about how to compute the normals of surfaces defined as level sets of functions. We can find this discussed in section 4.3 again. A level set surface can also be referred to as an implicitly defined surface. So for an implicitly defined surface, we don't actually have a formula for giving points on the surface. We have a formula that points satisfy. So in this case, I have a surface S, and an implicitly defined surface will have surface S is going to be defined to be the set of points x, y, z, satisfying h of x, y, z equals 0 for some function h. So you notice h is a scalar valued function, so we're just asking for that to equal 0. So for an example, consider the unit sphere centered at the origin. This can be the set of points x, y, z such that x squared plus y squared plus z squared equals 1. Okay, now this actually doesn't quite match the definition. The definition said some function equals 0, and here we've got some function equals 1. But we can do this by just changing the function to be x, y, z such that x squared plus y squared plus z squared minus 1 equals 0. And now this is now the h of x. Y, z is the function x squared plus y squared plus z squared minus 1, and the unit sphere is the set of points where that function is equal to 0. So for this, we have a very simple formula from multivariable calculus. Let me recall a definition for you. The gradient of h is equal to, we use the gradient of h is the h partial of h with respect to x, partial of h with respect to y, partial of h with respect to z. So the gradient is a vector valued thing, and it's a function of x, y, and z. So gradient h is vector valued, and strictly speaking it takes x, y, and z as arguments. Gradient h is gradient h of x, y, and z. And the theorem here is that for well-behaved surfaces, I'm not going to try to define everything that carefully, is if the gradient of h is non-zero, then the gradient of h is normal to the surface. So we can use this to compute normal vectors. For the sphere example, you might just think about the gradient, just to draw a circular version of the sphere. The h is the distance squared, so h minus 1. h of x, y, z is the distance squared from the origin minus 1. So you can see that the gradient gives you the direction of the maximum change of the function, and that'll be perpendicular to the surface, in this case going away from the origin. So it's the same kind of thing that made Lagrange multipliers work, for instance, in multivariable calculus. So let's do an example. So we'll do a couple simple examples. The first one is the unit sphere, which we just defined, centered at the origin. So here we have h of x, y, z is x squared plus y squared plus z squared minus 1. So the gradient of h is then 2x, that's the partial with respect to x, 2y, That's the partial with respect to y. 2z, that's the partial with respect to z. And this will be, it's clearly this is non-zero if you're not at the origin, which you're not ever when you're on the sphere. And this will be normal to the sphere. You do have to check whether it's going inward or outward from the sphere. Turns out these are normal vectors, not unit vectors though. Normals pointing outward from the sphere. To get unit normals, you could either divide by the magnitude, or you could notice that xyz, since it's on the sphere, is a unit vector, so if you divided by 2, you would get a unit vector. So very easy. So another example is the upside down parabola that we did in the previous lecture. So remember, this was the set of points on the surface, y equals 1 minus x squared minus z squared. So I'll use the following function for h. I'll use h of x, y, z equals y minus 1 minus x squared minus z squared. And of course that's equal to y plus x squared plus z squared minus 1. And then the gradient of h is the partial with respect to x, with respect to y, and with respect to z. So it's 2x, 1, 2z. And this is the same example that we had before, with the same answer, in fact, that we had before. You don't always get the answers that look the same if you do the level surface method versus the parametric function method. Sometimes the answers come out looking rather different, but assuming you've done everything correctly, you can always finesse it to see they're really the same. Possibly, though, differing by a scalar multiple, because this only gives a vector that's perpendicular to the surface. It doesn't necessarily give a unit vector perpendicular to the surface. In particular, this one is, in general, not a unit vector because y is 1, and then the x and z components are, in general, not going to be 0 except over the origin. That's it for this presentation. Thank you very much.